All right, so
This is the macOS version.
we're gonna pick up where we left off. We're gonna pick up where we left off. Kind of go over some stuff with the contingency tables. We'll go over some other kind of little things, and eventually we'll kind of do a bunch of work in Excel. So one thing we had talked about towards the end of last class was that if we were to take the area that was in each one of those circles, we said that represented A union or A or B, right? And then everything outside those circles, I said you had to kind of trust me, but then I did kind of give you an example as to why this is what it is at the end of class. But everything outside those circles, or kind of this light blue shaded area, is the intersection of the complements. Okay? Well, if we take the area of the circle plus that light blue area, that should always add up to 1. We then said we could rewrite this union as, does anybody remember how can we find unions? That was where we said, well, if we just add up the probability of each event, we're going to be double counting what's in the middle. What's in the middle or the overlap of those two circles is? Yeah, just the intersection. So if we count it twice, we'll subtract it out once, right? And then fill out the rest of this formula so that we know these 4 components will add up to 1. So here, if I'm looking for B, probability of B, I know the probability of A is 0.5. Probability of that intersection is 0.1. Intersection of the complements is also 0.1. Wait, no. Intersection of the complements is 0.3. Now it's just a little bit of algebra, right? So 0.5 plus 0.3 minus 0.1 is 0.7. So the probability of B is 1 minus 0.7 or 0.3. So basically just using that equation, plugging my values in, and it's just a little bit of algebra. Now, kind of what that hinges on is remembering that we can rewrite the union as the probability of each event add together minus their intersection. Also, sometimes people try to do this visually and don't write the formula out. And it's always kind of tough because it's easy from this to think of the probability of B as just this area here, but it's not, right? It's the entire circle. Right? So I've seen people try to do this in their head and they come up with the wrong answer, usually because they're, you're thinking of it just that dark blue area when in fact it's the entire circle of B is what we're looking for. Okay. So, right, we just plugged all those values in. Or I guess what you could do, you could rearrange it first for what you don't know and then plug the values in. I don't know. Either way, I think it's probably easier to plug the values in and then do the algebra afterwards, but either way, we kind of have the same values. Any questions on this one before we keep moving? Okay, so let me see. You guys can kind of do this on your own, right? So I'll give you a minute and a half, 2 minutes here. If I had a similar setup with the probability of A and the probability of B are not 0.3, the intersection, the probability of the intersection of the complements is 0.5, and I want the probability of what's in both, right? A and B. So I've got the same kind of setup, some different values. Give you a little bit of time to kind of work on this one, and then we'll talk about it. You guys see the board okay over there? Yeah.
Is the probability of B is like the whole circle?
Yep, right. So that's where we think about event A. So the probability of A is this entire circle. Probability of B is that entire circle. That's why I said sometimes the visual of these Venn diagrams can make it a little bit trickier. But if we kind of remember the formula that we have, using that formula, shouldn't be as good. go for like another 15, 20 seconds here. 2:15. All right. If you don't have an answer in, take your best guess. Get everybody in here right now. I think I'm picking up people from different classes. So everyone's okay? All right, I'm gonna close it out. So I use the exact same formula I did before, right? It's just now I have different values. So the probability of A here is what? 0.3 plus the probability of B minus the intersection, so that's what I'm looking for, plus the intersection of the complements, I think was 0.5, right, is equal to 1. So this one's a little bit tricky, right, because I have this negative sign. So I'm going to have to move this to the other side, right? So I end up with what? 0.3 plus 0.3 plus 0.5. I'm going to subtract 1 from both sides, and then I'm going to add the intersection of both sides so that I can get the probability of the intersection is just 0.3 plus 0.3 plus 0.5, which is 1.1 minus 1. So I should get 0.1. So like I said, the visual, like asking about, does the whole circle represent 0.3? That's where you can kind of get tripped up because you might look at this and say, okay, this area is 0.3, this area, I mean, this is all going to add up past 1. How's that possible? Well, that's because if the entire circle has an area of 0.3, right? So visually, when you're looking at just that white space, right? It's the you know, this is not 0.3. It's the entire circle. Okay? But when you're kind of writing out the equation and plugging the values in, that shouldn't trip you up there. Okay? But I guess this negative sign is a little bit difficult to deal with, right? So I wanted to kind of show you an example. If that's what you're looking for, it might be a little bit trickier. Okay. Any questions on that before we keep moving on? All right, so got everything up there we did on the board. Last class we talked about independent events, right? So we had this idea. One of the ways we can check to see if they're independent is if the intersection of the two events is simply the probability of each event multiplied by each other, because we had this multiplication rule we knew would hold. But if it's independent, the probability of B condition on A is the same as just the probability of B, right? So we know if they're independent, this equation not here should hold. We'll walk through an example on the contingency table where we looked at that. But this idea is kind of powerful, right? So we think about an example, and I guess we'll do this now before we do Excel. I might do the other stuff afterwards, but let's say, what do we want? We'll kind of use some of the things that we talked about to answer this question. So what if I want to know the probability that at least 2 people, and I say this class, I didn't use you because you guys aren't that big, in one of my conventional stats courses, which is about, I think I used 35 or 40 people, one of those two. So in a class of 35 or 40 people, how likely is it that 2 people in the class have the same birthday? So we're going to assume there's no twins, right? Because if there was, that makes quite a difference, right? And we're also going to have every day is equally as likely, right? So the distribution, if you look at every day, are equally as likely to be born, if you're just like choosing a person at random. So we're going to define X as that 2 or more people have the same birthday. Okay? So event X is that 2 or more people. So it could be that, 2 people have the same birthday, or, right, 3 people, and we would just be adding all those up. Well, notice they're mutually exclusive as well. I can only see exactly 2 or exactly 3 or exactly 4 people have the same birthday, right? So there's no intersections here. I'm going to see one number, right? So I'm basically thinking about X as just the probability I see 2 or more. So what would X complement be? Just the probability of seeing less than 2, which means no one has the same birthday, right? Less than 2 means every day there's only one person that has a birthday on that day. So our X complement here is really the probability that no one has the same birthday. So we're interested in what's the probability that two people have the same birthday. That was our event X. X complement is that no one has the same birthday. So we can find this. Well, then we could use that complement rule, where it would be the probability of X is just 1 minus the probability of the complement. Right? That was the idea that we said we got circle A and everything outside of circle A, that adds up to the entire experimental outcome space. So we'll use that complement rule. Once we find the probability of the complement that no one has the same birthday, subtract that from 1, and that will give us the probability that 2 or more people have the same birthday. So, if usually you ask people this question, in a room of 35 or 40, they generally think like the probability that 2 people have the same birthday is relatively low. And then you say, well, how many people, like, as I get more people, right, that becomes more and more likely. In a room of 50,000, it's very likely 2 people have the same birthday, right? So what number of people does that kind of surpass that 0.5, right? Or that kind of that half, the probability becomes greater than 0.5, right? So we can actually solve this. I already kind of mentioned we can use this complement rule. This helps us out. And now we're just going to find the probability of that complement, which is that no one has the same birthday. So if we think about this, we would go through every single person. And birthdays are independent. That was one of the things we started with. They're independent events, right? Unless, you had parents who knew each other and tried to like sync up having kids at the same time, right? Every birth is generally independent, like probably all yours is independent from the other, right? So for the very first person you look at, let's say I was going through my class of 40. The first person, what's the probability that they have a unique birthday? They're the first person I'm looking at. So the probability they have a unique birthday is 1. There's 365 days that they could have a birthday out of 365, and they won't have the same birthday as anyone I've looked up at up to this point. So the first person. So I now have that person, they have a unique birthday. Right? So there's probably nobody has the same birthday. It would just be probably the first person has a unique birthday, and probably the second person has a unique birthday, and just kind of adding those up. So the second one is going to be how many possible days could they have a birthday and have a unique birthday? Well, one of the days is taken now. So the probability they have a unique birthday would be 364 out of 365. Or 365 minus 1, because there was one person, they stole a date. Right? They took away a day so that, now I can't, in order to not have the same birthday, they couldn't have a birthday on that day. And the third person, now there's 2 days they can't have a birthday. So 363 out of 365, they have a unique birthday. And then continue to do this all the way up to, I don't know, I should change that from 38. This should be, or 58. This was supposed to be a classroom of 38. That's how big my little section is right now. So that's why that moves. And then I can think about, well, if every birthday is independent, what I really want here is that the probability that the first person, so person 1 has a unique birthday, and person 2 has a unique birthday, and person 3. Well, if they're independent events, I could just write this as the product, right? That each person that I'm looking at has a unique birthday. That kind of comes from this idea, right? The intersection of independent events is just take the probability of each event, multiply it by each other. Well, if birthdays are independent events, take the probability the first person has a unique birthday, times the probability the second person has a unique birthday, all the way down to the last person in class. So if I do that, right, I think here I have one big class, so we could stop this wherever we want. I think I had 308 here for a class of like 60 something, but if I did this for a class of 35, this always kind of breaks down to, we can actually use some of the, we haven't talked about factorials, but there's another way we can represent this equation. We'll get to factorials probably Wednesday or Thursday, Wednesday or Friday. But if I kind of rewrite something like this, and rewrite it before using these factorials. So what ends up happening if you multiply 365 over 365 times 364 out of 365, all the way down to like, you use a classroom of 60, you do a class of 35, whatever you want. A class of 35, that probability is at about 0.186. But remember, that's the probability that no one has the same birthday. So the probability that 2 or more would be 1 minus that, and actually about 0.81. So in a class of 35, right, you're already at a like 80% chance that two people in the classroom have the same birthday. And that probability just rises as you add more people in the classroom. I think that result's a little counterintuitive. In fact, the point at which you pass that 0.5 is actually at 23 people. Right? So 23 people is the first room size that actually, if you're like, putting money on this, right? What's the probability 2 people in this room have the same birthday? As soon as you get to a classroom of 23 or a room of 23 people, you should start betting what we call the over. Right? You should start betting that 2 people do have the same birthday, because that's more likely than 2 people not have the same birthday. Really, all this kind of came, I think it's kind of a fun example, mostly because it's a counterintuitive result. I don't think you would think it would be that high. But it really just takes like this idea of independent events, the idea of a complement. It's a little bit harder because we're defining the events a little bit goofier. I don't know, I think it's a kind of fun little example. We'll go through some of this stuff here in a second. I'll show you this after we work through some Excel. Okay. So, I must be getting old and making noises when I sit down. All right, so I have, where is it? There we go. A union data file up on Canvas, right? So it's underneath that in-class data folder under files, and it has 2 sheets to it, right? So one is blank, and this is the one that hopefully we're going to recreate, okay? I might use some different values, my cutoffs and stuff, but I'll try to kind of keep it exactly the same. So I've got this already zoomed in a little bit, but this is more of a business statistics example. I usually like to use things that I find more interesting. This one is kind of interesting because it has like an economic spin to it. So I've got 10 different years for all these different industries. So notice I already had this data filtered. So I think last class I showed you how to filter data. So we just started the first kind of variable label, Control Shift, Command Shift on a Mac, hit the over, the down arrow, go to data. I already have this filter option selected, but if I didn't, right, and the data came in like this, when I hit that filter, it throws in those arrows for me. I've got different variables for each one of these industries, the percent of that industry that would belong to the union. I have the union member weekly earnings. I have non-union member weekly earnings in that industry. And then I created this variable, which I called the difference in earnings, right? So all I did here was take union wages, subtract non-union wages. So the idea of a union, right, is that you're trying to give, some of you are in 201 right now, but some of you have already taken 201, right? So like, did Professor, now almost called my first name, did Professor Nesson go over monopsonies at all? Do you remember that? Sometime he might have skipped it. Okay, so just like, but you probably talked about monopolies, right? So you can talk about things like monopoly power, and that's when one industry has complete control over selling of the product, right? One producer. Well, when you have a union, right, your workers are, you can think about it as they're supplying the labor, right? They're no, like we usually think about consumers like that's demand, but they're supplying the labor, and so they can kind of monopolize it if they come together and say, well, we're not going to work, no one in the union is going to work for any wage less than this. So it should be that this union power is causing this difference in earnings to go up. So the higher the percent of an industry is unionized, the more power they have to increase their wages above what their wages would be if there was no union. Right? So with this idea in mind, like this relationship between the percent of an industry that's unionized and what the difference in union and non-union wages are, we can kind of explore this a little bit. So, because you can imagine, if not many people are in the union, I don't have to pay the higher union wages. I can just go out and get someone who's not in the union. Right? So these different industries, the unions might have more or less power. So I'm going to choose some cutoff values. Like I said, I want to make sure these match up. So I think I chose 10 and 100 here. But we'll see how I got there. So what I will first do is, okay, what is the mean kind of union membership across these industries? So I'm going to use this average function. I'm going to go over and use the union member percent, right? So the average percent of these industries that are in the union, Control Shift or Command Shift on a Mac, hit the down arrow. I find on average across the industries in this data set, 10.7% of the workers are in a union, right? Now, some, are very low, others are higher, but the average is about 10.7. I'll then kind of look at, I could find the union earnings or non-union earnings, but for here, the one that I'm going to actually worry about is what is this average difference in union and non-union earnings, right? So I'm going to take this difference variable, find the average, right? So on average, the difference is about $118, right? So union members make $118 more. And I don't remember if I think this is weekly, right? So I just chose the cutoffs of 10 and 100 because they're relatively close to those means, but they're kind of nice, easy cutoffs, right, to look at. So I'll say, okay, I want the cutoff of union membership to be 10%, the cutoff for the difference in union and non-union earnings to be $100. Okay. So I might be interested in things like, okay, well, what's the probability that one of these, if I choose an industry in random, that the difference is greater than $100 and their union membership is actually less than 10%. Excuse me. So how do I find these probabilities, or how do I build this joint contingency table where I've defined my events as being, is the difference in union and non-union earnings $100 or more or less than 100? Kind of like my A and A complement. My event B I've defined as, does the industry have 10% or higher union membership, or is it below that? That's my B and B complement. I'm just creating one of those tables that we kind of already looked at. I'm just putting actual names to the events now. It's not A and B. So how can I do this, right? Where do I get those probabilities from? Well, the first thing that we're going to have to do is determine from our data set how many observations or how many industries here belong to the group of, did that industry have 10% or higher union membership, and was the difference in union and non-union earnings more than $100 or $100 or more? So I'll first get my frequencies, and then I'll think about how can I turn those frequencies into probabilities, okay? So first we'll do, how can I find my frequencies? You can go back and use that Countifs formula, okay? So that Countifs formula, when we're doing it with histograms, we use it a little bit differently than how we're going to use it now. So we now have two variables we want to look through. The first variable, or the first range of data we want to go through, is this union member percent variable, right? So we'll highlight that variable, use that control shift or command shift on a Mac down arrow, and it puts in that range of data, okay? Comma, the second thing we're going to tell it is, okay, what's our first criteria? Well, we want to count up the number of industries here, or the number of observations, where when I look through that union membership variable, and I hate that it does this. I should have put another row in here, but right above me here, I had this 10% or higher. So I'm going to say I want to count it if it's greater than or equal to, and then I'm going to use an and sign, and instead of putting the number 10 in here, I'm going to use this cell that I put the 10 in up here. That way, if I want to change it moving forward, I can, and everything I do from here on out will update as well, okay? So look through that union membership data, or union membership variable, sorry, comma, count it if it's greater than or equal to this value of 10, which represents 10%, okay? Oops, comma, then I'm going to select the second variable I'm interested in here, which is this difference, right? This difference in union and non-union earnings. I could highlight this again. I don't like to scroll back up because then you guys have to watch it and it's probably nauseating. I know it's the same range, but it's going to be in column H. So I'm just going to type here H2 colon. So that means go through H2 all the way to all the way up to H736. Just matching those values right from the first one. So now it's going to go through this difference earning variable, and it's only going to count the observation if it's $100 or more. So greater than or equal to, then I have to put that in quotation marks, use the and sign, my cutoff of $100 that I had up here, okay? Any questions over any of that? Right, so now I'm gonna go through, I'm gonna look through that union membership variable, only count the observation if it's greater than or equal to 10%, but then go back through the difference in earnings variable, and I'm only going to count the observation if it's greater than 10%, and now if that difference in earnings variable is greater than or equal to 100, right? Kind of have two criteria set here, but now instead of using the same variable to set both criteria, I'm using two different variables to set those two different criteria. It's a little bit different than the way we used the Countifs before, but same general idea. So if I hit enter here, this should give me the number of industries that have union membership of 10 or higher, 10% or higher, and have a difference in union, non-union earnings of $100 or more. Okay. I then want to go through the different combinations, right? And count up the number of industries that have union membership below 10% and have a difference in earnings of $100 or more, right? Remember, these top four left cells, we're trying to eventually build a contingency table. Well, those all represented intersections. So I want to count the number of observations where this and this is true. So I'm going to be using this Countifs formula. You can type it in like to each one of these different combinations of the row and column headings. I think an easy way to do it, instead of typing it all in, it's really going to be the same setup. It's just that I'm using the same cutoff values. It's just that I'm going to have to be careful with my equalities, right? And change the direction of like, well, now I want to know, is it less than 10% union membership? So I'm going to highlight this. If I copied it over, I'd have a problem, right? Because things are going to update. I got to figure out, okay, I got to freeze all these. I'm going to go put $ signs in front of all of them. You can do that, right? Another shortcut would be if I highlight this and copy it, and then I go over and click on the cell I want to paste it into, right? Notice none of these cell references have updated. So if I just use my mouse to drag it over to copy, that's when it updates my cell references. If I go through and like use my mouse or use the shortcuts of copy, like highlight it and copying it and then go to the cell and paste it, it doesn't update anything. So that's one way you can do it. The other way you can do it is just highlight everything and start hitting, start putting $ signs, hitting F4 or Command T on a Mac and putting $ signs in front of everything. Now, when I copy this over, I'm getting the exact same thing, right? And then I could also copy this down and I'm getting the exact same value, right? Because I just froze everything. If I freeze every cell reference, it's just going to keep doing the same thing. But obviously I need to change those because in this group, for instance, well, I'll do this one first. This category, I now want to count the number of industries that have 10% or higher union membership. So when I'm looking at that union membership, I still want to know, is it greater than or equal to that 10% cutoff? But now when I look at that difference in earnings variable, I only want to count it if it's less than $100. So I have to go in and change my equalities to make sure they match up with my row and column headings, okay? And actually, let me double check here. My paranoia is getting the best of me. Okay, I was gonna say, I wanted to make sure I started this recording. I then go to this group, right? Well, this is gonna be the number of industries that have below 10% union membership, and the difference earnings will be less than 100. So now both of these I want to change to being less than, right? To match up with that row and column heading, okay? Any questions over what I'm doing here? I want to lose you guys at this point. We okay with this? Basically just using that Countifs, it's going to be the same cutoffs. This one's going to be below 10%, but greater than or equal to that 100. So I get to leave that one the same, but change the equality over here because I need to make sure it's less than 10%. And now I've got all these frequencies. Right? So just looking at the frequencies, you can get an idea. Well, if my union membership is 10% or higher, it's much more likely, right? There's 220 industries where they get a difference in earnings of more than $100, and only 67 of those industries that have high union membership have less than $100 differential, right? Only 67 of them. So you can kind of get an idea on the frequencies. It looks like having high union membership, it's going to be more likely that you have a pretty big difference in union and non-union earnings as well. But we can kind of get the probabilities eventually here. I'm then going to find my totals, which if you think about it here, For the for the industries that have union membership of 10% or higher, well, that would just be all the industries with 10% union membership or higher and a difference in earnings of $100 or more, plus the industries that have 10% or higher and have less than 100, right? That covers every possible industry that has more than 10% union membership because they have to belong under one of these categories. The difference is either $100 or more, or it's less than 100. It's in one of those groups. So to get these totals, just like with the contingency tables, I said if I didn't show you the totals, you can just add across the rows or down the columns, adding up those intersections. All right. So I'll just add up these two values. Whoops, let me move this out of the way. I'll add up those two values. I'll drag it over. I can do the same thing for the below 10% industries. I can add across the rows. So use that sum function to add across the rows and then copy that down. And now hopefully if I add up these two guys, well, if I'm adding up the number of industries that have a difference in earnings of $100 or more, plus the industries with less than 100, that's gonna, every industry has to be in one of those categories. Those should add up to the total number of observations, right? So I can do a check here using that count function, and hopefully the number of observations I have is 735, right? So I go back over here, select that variable, hit enter. I can scroll over and show you. Sure enough, I did everything correct here. Right? If I had made a mistake, like let's say here, I had forgot to change one of these. Oh, I did something wrong, right? I'm not matching up the total number of observations. So, okay, I forgot to change this one to a less than to match up with this less than $100 and less than 10%. And now I make sure that I'm getting that total number of observations correct. So I went through that a little bit quicker. Does anyone see one of those cells again or have any questions? So we've built this frequency table, right? And I think, I don't know, in the next Excel homework, I might call this like a joint probability table, or sorry, I might call this a contingency table. And then from the contingency table, I was kind of using that term a little bit loosely when I was showing you the ones with probabilities. Generally, we would then call it a joint probability table when we look at the actual probability. So how can I turn these frequencies? So I'll show you what I did here, especially for like that first Excel assignment. I just copied this and pasted it and then deleted the numbers so that I could just get the same setup here and just all the same labels. I have my frequencies and I want to turn them into probabilities. So I get this joint probability table or this contingency table that we've been working with in class. Right? How can I do that? Well, if I know the number of industries that have 10% or higher union membership and a difference in wages of $100 or more, and I know the total number of industries in my data set, how could I come up with a probability here using the empirical method of assigning probabilities? Simply do what? Yeah, I know if there's 221 industries that fit this criteria out of 734, 221 divided by the total number of observations, that's 735. I then basically do that for every one of these categories. I just divide it by the total number of observations, and that'll turn my frequencies from a data set into probabilities. It's basically like what we did when we had frequencies and turned them into relative frequencies. Relative frequencies, I think I mentioned this last class, are really pretty synonymous with just probabilities. That's what they were, right? And so we can kind of think about those two things as the same. So when I go through and do this, if I want to divide everything by the total number of observations, I don't want to have to enter this in a million times. So what can I do here? Yeah. Yeah, right. If I just, if I can type. Come on. There we go. If I put my dollar signs in front of that row and column, it freezes it. Now when I copy this over and down, it'll keep updating that frequency, but not the total number of observations, which is what I want it to do. And hopefully, if I do it correctly, I should get 1 right here, right? Because this should be the total number of observations over the total number of observations. Okay. So that's how you can basically produce your own joint probability or your own contingency table. So that the vaccine kind of COVID data, like when I showed you, that came from basically doing something like this. You went through a data set of all these individuals who developed COVID and whether or not they died and whether or not they were vaccinated. And you just use this Countifs function to build this contingency table. Okay. Any questions on that process? So you first have to find your first have to find your frequencies, and then you can turn those into probabilities. So anytime we're talking about probabilities, it's also going to be synonymous. You could think about this as just like the number of individuals in each one of those groups out of the total, right? Total number of observations. So from this table, right, what's the probability that if I chose an industry at random, that it has 10% or higher union membership? What would that be here? You can tell me to the second decimal. Yeah.
Used to be 0.39.
Yeah, right. Those totals represent the probability of the events themselves, the row or column heading. So these totals represent the row and column heading probabilities. So probably being 10% or above, I look at that 10% or above, go down to its total column, it's going to be that 0.39. Okay. So we did some of this last Friday. All right. What's the probability that I see if I select an industry at random has 10% or higher union membership and the difference in earnings is $100 or more? So there, what value would that be? Yeah. Yeah, those top 4 left cells represent intersections. So I go to 10% or higher, $100 or more, this guy right here. All right. A little bit trickier. We kind of remember, if I want the probability of this given this event, right? So that was where we said, I want the probability of A given B. Does anyone recall how we could write that? So that was just take A given B. That was kind of like when we said, okay, we know B has occurred. So instead of the entire experimental outcome space, the space we're left with is whatever we conditioned on. And then the only area left that's going to have outcomes in event A would be wherever A and B overlap. Right? So this was the equation that we had that gave us a conditional probability. So here, my event A is being $100 or more wage differential. My event B is I'm conditioning on it has greater than 10% union membership. So I'll look at the intersection of those two things. So $100 or more wage differential and 10% or higher. So that was this guy right here. And then I divide it by whatever I conditioned on, which was simply being above 10%. We'll go to the total for that event that I was conditioning on. And I get about 0.76 here. Right? So given that an industry has high union membership, right, 10% or higher, the probability that they get this differential in union, non-union earnings to be $100 or more is about 76%. Right? So which would mean, it's kind of maybe foreshadowing some stuff here. But what if I wanted the probability, I'm going to copy and paste this over here, blow this up for a second so we can see it. What if I wanted that exact same thing, but now I want less than that $100? So I'm conditioning on the same group, right? But now I want the probability that the difference is less than $100 in that wage differential. Well, if you think about it, once I've conditioned on the same thing, there's only 2 outcomes, right? Once I say, okay, look, we'll only look at the industries that have 10% or higher union membership. Now, given that you know you're looking at one of those industries, what's the probability the wage differential is $100 or more? And given that you're looking at those industries, what's the probability it's less than 100? So what do you think these should add up to? Yeah, 1. It's the only 2 possible outcomes. Well, we can prove this to ourselves. Because we can look at these events, take the intersection of these two events, right? If we treat this as A and B, so the probability that we make less than $100 wage differential and it's 10% or higher, divide that by the probability of what we're conditioning on, which is being 10% or higher. And sure enough, those two would just add to 1. So if you're conditioning on the same thing, right, and you only have 2 possible outcomes for your other event, those 2 probabilities should add up to 1 there. Okay. So I could have saved myself a little bit of time. I guess I did 1 minus this instead of plugging things in this equation. Really, it doesn't matter. It gets me the same answer. Right? But then I can also look at like the other side of things. So now, given that that industry has below 10%, what's the probability they see a high wage differential between union and non-union earners? We can look at the intersection of these two. So more than 100 wage differential, but below 10%, divided by the probability of what we're conditioning on. We're now conditioning on the industry having low union membership, right, or below 10%. Oh, not equals, divide, right? So I can find all these conditional probabilities. And this is interesting because what this is really telling me is that, look, if you're looking at an industry that has high union membership, the probability that those union workers can drive their wages up more than $100 from what they would be if they weren't in the union, 76% chance. However, if you're looking at industries that have low union membership, those unions have much less power. And so the probability that they can get their wages to be more than $100 higher from not being in the union, only about a 40% chance, right? So you can start to answer some like pretty interesting questions once we calculate these conditional probabilities. How did we get these original, how did we get the probabilities to do that? Well, we first had to start with frequencies. Basically use that Countifs formula, get your frequencies that belong to each one of these groups, use that empirical method where you're using historical data to come up with those probabilities for predicting the future, turn those frequencies into probabilities, and then it's just all the rules and stuff we've been talking about. Okay. Any questions over anything we kind of did here in Excel? Can you see, like, hopefully the usefulness of being able, can you imagine having a gigantic data set with like, survey data or something of individuals with tens of thousands of observations? You can then look at like what actually happened to build these probabilities and like really get at some pretty interesting questions.
Can I see the formula for
J20, wait.
24,000. Yeah.
Yep, we're just taking that intersection and dividing it by whatever we're conditioning on.
Okay.
Yep.
Thank you.
The probability of whatever we're conditioning on. So we're okay with this. So I will work on getting it up this afternoon. It may not be posted until tomorrow. But I'll wait till tomorrow because you guys technically can work on the Excel assignment right now to the end of the day, right? So I'll get it posted either tomorrow or I might wait until after class Wednesday. But the next Excel assignment, a large portion of it will kind of be building these probability tables, or I might turn it into an individual assignment. So you'll get one of those here posted tomorrow. I'll make my mind up here in the next 24 hours. But I want to go through a couple more things before I let you out, which are just interesting ideas related to what we've talked about. We're going to talk about Bayes' theorem tomorrow, but there's this kind of fallacy. So it's kind of somewhat relevant to my life right now because I've gotten into sports gambling. That's a problem, but not like a big problem. Okay, let's calm down. But there's this thing that people when they gamble fall victim to, and I put Kenny Rogers fallacy, but it's the gambler's fallacy, right? Yeah, know when to hold them, know when to fold them. If I'm flipping a coin, every time I flip that coin, the probability that comes up heads is 0.5. It doesn't matter, right? If I flip a coin that comes up heads, the next coin flip, the probability it comes up heads is still 0.5, right? Previous successes don't impact future probabilities of that success, right? Or here successes sitting heads. So if coin flips are independent, right? The answer is that the probability of getting a heads after you just got 10 in a row is still 0.5. In fact, you can run these simulations in Excel and you can prove to yourself that like use like a random number generator, 1 and 0, basically 1 being heads, 0 being tails. And every time in the data, so you can do a simulation of 10,000 coin flips. And so I actually did this. And then you take, after you see a tails, the probability that the next flip is a heads is about 0.5. Every time in the data you see 2 tails in a row, the probability it comes up heads is a little bit right around 0.5, a little bit low. 3 in a row, 4 in a row, it's really just oscillating around 0.5. If we had an infinite number of coin flips, this would end up being exactly 0.5, right? But we've got a sample, right? So just kind of really close, but it doesn't matter. 1, 2, 3, 4, or 4 in a row come up tails, it's no more likely the next one comes up heads. But people fall victim to this because like, well, you know, in the long run, 50% of the outcomes will be heads, 50% will be tails. So you keep thinking, well, I saw 4 in a row, it has to be balanced out. Well, not necessarily on this next coin flip. Right? You know, it might be balanced out over the next 1,000 coin flips. Right? So there's this really famous example back in the turn of the century. Right? So roulette table, for all intents and purposes, there's one thing that's not red or black, right? Generally, it's 50% red, 50% black. People on whether or not they think it's going to hit black or hit red. Right? It's this little ball that spins around. So black came up with this casino 26 times in a row. Right? So each time, right, and you know, it's an established casino, regulated, so they know it's like a fair roulette table. Well, when black came up 13 times in a row, everyone's like, well, we know it's got to be 50% in the long run, so it's got to come up red the next time. So everybody bet red, right? Thinking it's going to balance out. Well, it hit black. Okay, well, it's got to hit red next time. It's 14 times in a row. Everyone bets red, doesn't show up red, it's black again. People kind of fall victim to this gambler's fallacy, all, you know, and it just, because this is a very rare event. It would come up this many times in a row as black. And basically people lost a ton of money. You know, everyone kept betting on red. The casino made a bunch of money off these people's incorrect gambling behaviors because each spin is independent. The probability it came up red every single time was 0.5. Right? We see this in like all kinds of things out in the world. Actually, Professor Ness and I just got a paper published last year about people think that it exists in like sports things. So like shooting a basketball and things like that. You can actually prove that there's like, both beliefs are incorrect, that making a shot, right, doesn't change the probability you make the next shot at all. Right? They're independent events. Right? Same kind of idea if I'm spinning a roulette table or I'm flipping a coin. And what this really comes down to, also it's kind of interesting here, to get the probability that it came up black 26 times in a row, we can do kind of like the birthday thing. Probability the first spin was black is 0.5. And the second spin was black, so 0.5 times 0.5 times 0.5, all the way up to 26. So you'd have 0.5 to the 26th power. So how unlikely was it to see this result at the casino? We could actually do what? 0.5 to the 26th power. I mean, this is e to the -8 means move that decimal point 8 places to the left, so 0.00000001. Right? That's how likely it was of that. And that's just kind of using some things we've talked about independent events. Look for that next assignment after today. Focus on the ones that I did today. Right now, if you have any questions, I'll be in my office. We'll grab some lunch. I'll be back around 2:30. 2:30 to 4, I'll be in my office if you want to stop by. Otherwise, I will see you guys on Wednesday. Okay?
Yeah, I realized that.